Hey everyone, so in this video, I'll walk you through gradient descent. So I'll take you through the intuition behind gradient descent, the algorithm, why it's important in data science, and I'll end with an example. So what is gradient descent? So let's start off with the idea. Gradient descent itself is just an iterative algorithm that minimizes functions. So you start at some initial set of parameters and iteratively move towards the set of parameters that minimize that function, your function of interest. So more formally, you start at some theta t. Theta is your set of parameters and t at time step t. So you start at theta t, and at each iteration, you get an improved version. So after one iteration, you get an improved version, theta t plus 1. So what is the idea that gradient descent really uses? How does this work? Well, let's take functions in general for a second. So gradients of any function, the gradient moves along the direction of steepest ascent. So that means that the negative of the gradient moves along the steepest descent. And remember, we're just trying to minimize functions, right? So gradient descent takes advantage of this fact. We just take the gradients of our functions of interest and take the negative of that and move in that direction until we find our minimum. So an analogy I like to think of is, say you're on the side of a mountain, right? And you're trying to get to the bottom of this mountain, but you can't see in either direction. So you don't really know the shape of this mountain, where it ends, where it starts, nothing. All you know is which way up is and which way down is. That's all you know, and you're trying to get to the bottom of this mountain. And gradient descent is the algorithm that'll take you from your point to the bottom of that mountain. So this is nice and all, but how does the algorithm itself actually work concretely? So first, you start off gradient descent by initializing your parameters. So theta 0, the values you assign however you want. They can be 0, random, whatever. And for each time step t from 0 to until you converge, you update your parameters in the following way. Theta t plus 1, that's at time step t plus 1, is assigned to theta t, your current set of parameters, minus alpha times the gradient of your function evaluated at those current parameters at time step t, so theta t. So again, theta t plus 1 is assigned to theta t minus alpha times the gradient of your function evaluated at theta t. And in this case, alpha is your learning rate, which is just a number between 0 and 1. So before we move any further, there's something important to address. An important assumption that we're making is that our function is convex. So first, what does that mean? What makes a function convex? Well, if you were to take any 2 points on a given function, so let's look at this function. If you were to take any 2 points on this function, draw a line between those points, that line that you make must always remain above the function itself. So if I were to take this point and this point, the line that forms between those 2 points, see, notice how the line is above the function itself. So I can take any 2 points, and this line will always be above the function. And that's why this function is convex. But notice, in this function, if I were to take this point and this point, the line falls below the function. Hence, this function isn't convex. So why are we talking about convexity? Well, remember, your gradient descent basically finds the minimum point of a function. And if your function is convex, then you find the global minimum or the true minimum of the function as a whole. And the reason this is important is because if your function isn't convex, then you might fall at a local minimum, like here, rather than the global minimum. So an assumption that we've made is that our functions are convex, hence we find the global minimum. So why is this important for data science? Well, remember, in data science and machine learning, you're really concerned about making predictions, designing models to predict something, right? So the flow kind of goes like this. You observe some data, design a model, say y equals x1 theta 1 plus x2 theta 2. You choose a loss function. We've seen many in class already, lasso, L2, etc. And your loss function, remember, is basically what tells you how good your model is, right? It takes some combination of your prediction and the actual observed data. And you want to get as close to the observed data as possible, right? So it takes these two values and finds a difference of some sort. And that's our function, right? We're trying to minimize that value because we want our predictions to be as close to our observed data as possible. So the way we minimize that loss function is using gradient descent. So gradient descent is what makes your models, your predictions get closer. It tunes the parameters of your model, in this case theta 1 and theta 2, in such a way that we're able to minimize our loss function to make our model even better. So let's look at an example of gradient descent itself. Let's take a simple function, y equals w squared. And we know that this is basically a parabola, right? And so the minimum is w equals 0. But let's pretend like we didn't know this. How do we arrive at that minimum value? Well, let's use gradient descent. And I've written the formula here just for convenience. So in this case, let's say our alpha value, our learning rate, is 0.1. And the derivative of our function is 2w, and our initial w value is 10. So after our first iteration, we see that w1 equals 10, which is our initial w value, minus learning rate times 2 times w, in this case 10, and we get 8. After our second iteration, we do 8 minus learning rate times 2 times w, and we get 6.4. Again, a third time, 6.4 minus learning rate times 2 times w, or 6.4 again, and we get 5.12. So as you can see, with each iteration, we're actually getting closer and closer to our minimum value of w equals 0, right? So it seems that with each iteration, we get closer and closer to that value. So let's see how well we actually do, say with 100 iterations. So I'll just launch terminal, launch Python, and let's take this exact example once again. So we started off with w equals 10. And now, let's say we do 100 iterations. And we update our w to be w minus learning rate times 2 times w. And we want to print w at each iteration. All right, so let's see how we did. So we started off, first iteration we got 8, second iteration 6.4, third iteration 5.12, which is exactly what we got when we computed it by hand. But now let's see, if we do this 100 times, we see that we arrive at a number that is extremely close to 0, right? So hopefully this convinces you that gradient descent does truly find the minimum point of your function. Hope this helped. Thank you so much.